Welcome to the second part of graphs of rational functions. This is regarding a file that we'll be posting on Office 365 titled Graphs of Rational Functions. The writing is already on there, so you will actually see that some things have been cancelled out. I'm just referring to exactly the file that you will see on the class website. When we graph rational functions can be of any form. I've actually seen throughout this chapter how we can have a function like this, x squared minus 4 divided by x minus 2, where we can see that we can somehow simplify it. Now that will create a problem when we're graphing it. And the problem is, when we look at the original function, first of all, in this video you will see that we're going to be looking at 3 cases for graphs of rational functions, what kind of problems we can see, what we can encounter, because the nature of the rational functions, how they can be simplified. When we look at a graph like this, a function x squared minus 4 over x minus 2, we could see that right away that there is a restriction and x can't be 2. So we know x cannot be 2. We know that. I'm actually going to write it down. X can't be 2. Okay. However, if we actually look at when we go ahead and simplify it, this is difference of squares, so the numerator is going to be x minus 2, x plus 2, and the x minus 2 and the x minus 2 will cancel out, and we're going to end up with x plus 2. Now what is this function? We know right away that that is a line. In fact, if we actually graph it, and let me remind you while we're talking about graphing, and you can check things online, that you can go to Desmos. You can go to Desmos.com, and the problem with the Android version of Desmos is it's not very clear, so you actually see that the grid kind of overlaps like that. It's not as good as the iOS or the iPad version. Anyways, so what we could do is then I'm going to put that function x plus 2, x plus 2, and you can see that that is a line. That's a line right here. Okay, so I know you're probably thinking Miss Musa is trying to show off right now, but okay, so this is what I have right now. Okay, now why is this a problem? Because we know in the original restriction that x can't be 2. But if we actually look at the line, there is no restriction on the x. X can be any real number. So what we do then is we have to place a hole at x equals 2. So we go to x equals 2, we go up to the line, and we place a hole. Meaning that, what does that hole mean? It means that there is no value right here. There's no value there. Okay, so the x's actually get closer and closer and closer, so they can be 1.9999999, they can be 2.000000001, and so on, but never really ever 2. Okay, so this is the first case where this case right here, where we can have a hole, because what happens is that the only restriction in the denominator got cancelled out. Okay, so the second case is that already some of the rational functions are already simplified, and so we don't have the problem where any of the restrictions will cancel out. So in this case, there are no holes for this rational function. It's just simply just like how the first video, that means it is a rational with asymptotes where x is equal to 5, which is that vertical line right here, and has not been shifted up and down, so the horizontal asymptote is y equals 0. The third case, which is what if we have this rational function, for example, x minus 3 divided by x squared plus x minus 12. When we factor out the rational function, we'll end up with two restrictions in the denominator. The x can't be 3, that comes from this bracket, and the x minus 4, which comes from this bracket. So we know that these are two restrictions. However, it is only the x minus 3 restriction that got cancelled out because we had that binomial in the numerator. So what happens is that we ended up with a rational function, just like case 2, which you should expect the asymptote to be at -4, because that is a horizontal shift to the left 4. So we actually have that asymptote x minus 4, and there is no vertical shift, so the horizontal asymptote is y equals 0, and so we have that case, just like case 2. However, if we look at the restriction x can't be 3, it's not represented in the graph. Well, yet, unless we put the hole in here. So because of that restriction not being accounted for in the graph of 1 over x plus 4, we had to go and place a circle or a hole where x is equal to 3, just to tell everybody that this graph can be any value except for 3. It can also be any value except for -4, but that is already represented by the asymptote. So this example right here is just another example that I have put previously. So the general idea, okay, what I really want you to get at in this case is that sometimes because restrictions can be cancelled, we need to use holes on the graphs. That is the general idea. Okay, we need to use holes on graphs. Whether we end up with a rational function like this one or a straight line like case 1. Whenever we have a restriction that disappears, because that restriction x minus 3 was originally in the denominator before we canceled things out. Because it got cancelled, we still have to account for it visually on the graph by using the hole. And that's it. Thanks for watching.